Hello students, in this video we will be discussing the motion of the electron inside a conductor when we apply potential difference across it and when there is no potential difference across it. So first we take the case of no potential difference across this conductor. All the free electrons inside this conductor has got the effect of the temperature. The temperature will induce the kinetic energy into these electrons, and which imparts a random direction, motion in random direction. So this electron moves in random directions and finally comes to the initial point, making its net a displacement to be zero, and net net displacement is zero, we can call that velocity to be zero. Speed is not equal to zero. Now the same thing when this conductor is connected across a battery of voltage V. Because of this voltage V, this electron, because of this battery V, there is an electric field induced. There is an electric field induced inside this conductor. Because of this electric field, there is a force with which the electron is pulled towards the other side. So the electron finally, after its random direction, it will not go to the initial point, but it will displace this much displacement in the direction of the force, so giving its net displacement not equal to zero, and this velocity with which the electron moves, velocity with which this electron is moving, is called drift speed, which is also not equal to zero. Speed is not equal to zero. Here we have to remember this velocity is very much less than the speed of the electron for a simple reason. The velocity, with this velocity, it has to cover only this much displacement, whereas with the speed it has to travel this larger distance in that same time. I hope you understand this example. We have discussed this example in the class. Second point, how to calculate the speed with which these electrons are moving. That speed we called as a drift speed. You can take this conductor. Let's take the cross section area of this conductor to be A. Let's take n number of electrons are present at one instant, which are moving with a velocity of drift speed. After some time t, all these electrons get shifted by this much of displacement. This displacement can be written by drift speed into time. Current is a rate of flow of charge. Rate of flow of charge in the conductor. The charge flowing in this volume is given by number of electrons into this volume. So current is equal to total charge is number of electrons into the volume, area into the displacement upon the time. We can also write this one as I is equal to NA. Displacement is given by Vd into T upon T. So from here we get the famous equation of I is equal to NEAVD. From this equation we can calculate the drift speed. There is a special term called current density, which is defined as the amount of the current passing through given area. Let us continue our discussion with this drift speed as follows. The displacement of an electron the average displacement of an electron between two successive collisions. This displacement we call as a lambda. Lambda is called mean free path. Mean free path. And the time it takes to travel from here to here, this time we represent by factor of tau. We call this time as relaxation time. Relaxation time is the time with which the electron takes between two successive collisions. Here, if this electron is expected to travel with the speed of drift speed, we can simply write this equation of displacement is equal to drift speed into time. We can substitute the value of drift speed. Vd is equal to lambda is equal to Vd, I can write as I upon Ne into A into T. So from here I can calculate the lambda value. Thank you. There is a small correction. This T has to be replaced with tau. The equation becomes like this: I upon NEA into tau. Fine.